In this lecture, we're going to talk about the definite integral a little bit more, so it's definite integral part 2. In particular, we're going to take a look at the actual definition. So let's review a little bit from last time. So last time I wrote down this expression, the integral from a to b of f of x dx. And when you see this, when you see the definite integral, or when I say integral, you should think immediately this is the same thing, this is equivalent to area, because that's what the integral gives us. So I say integral, you say area. Just like when I say derivative, you say rate of change, and vice versa. So if you want to think of this, this is actually equal to, if you want the area underneath f of x from a to b. And it's probably better if we draw a picture of this. So down here, let me draw a picture to sort of illustrate this. So here's my function f of x. And we're looking at the area from a to b. And we can even use a different color. So that bunch of symbols up there represents this area in yellow right here underneath the curve, of course. So last time we talked about this, and this time what we want to do is we want to talk a little bit more about what the actual definition is. So the way that you can define this integral from a to b of f of x dx is just like last time. To figure out the area, we're going to do these little sort of rectangles. So the idea is to break this interval up into smaller intervals. So we can put, let's say, x sub 1 here. We'll call it a x sub 0. And then we can make another one, x sub 2, x sub 3. So we're just going to break this up into equal parts, and then we'll have x sub n equal to b. And what we can do then is we can make these little rectangles here. So we can make a rectangle from here to there. We can make a rectangle from here to there, and make a rectangle here to there, and so on. So dot, 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 and then we'll have our last one right from here to right there. So a bunch of little rectangles, and we can add up their areas. So this would be, if we want to approximate it, we just take this height, which would be this would be the height f of x sub 1, would be this height right here. And let's color code this. So this height right here would be f of x sub 1. So I'd have f of x sub 1. And then that's the height, and the length right here is just, we'll call it delta x. Right, delta x is the length of each of these little sort of segments. So delta x is actually, you can find this by taking the length of the interval, b minus a, and divide it by n. Right, but for us, it's good enough that you recognize that this is delta x, that length right there. So you take delta x times the height, f of x1. This height over here is f of x2. And so you'll add the area of the next triangle, so f of x sub 2 times delta x. So that's going to give me the area of that rectangle there. And then the next one is going to be f of x sub 3. That's this height here. So you'll add that one. So it'll be f of x sub 3 delta x plus, and you keep doing this dot, dot, dot until you get to the last one. And the last one has height f of x sub n. So you'll take this height, again, times this length, which again is delta x, and you'll get the area of the rectangle. So plus f of x sub n delta x. Now this is just an approximation. As n gets larger and larger, you get a better approximation. So if n is 100, that'll give you one estimate. If n is 1,000, that'll give you a better estimate of the area. If n is 1,000,000, that'll give you a better. So what you can do is take the limit of this thing and let n get bigger and bigger, so you let n go to infinity. And so this is the actual definition of the definite integral. So this is the definition of the definite integral. It has a closed form, so the closed form is the integral from a to b f of x dx, which is equal to the limit as n goes to infinity. In the closed form, you kind of write this in a little bit sort of shorter notation. So here you can have I equal to 1 to n of f of x sub I delta x. And this is just a fancy way to write this above. So this expression right here is really the same as this expression right there. Sometimes this thing highlighted in green is called what's called the Riemann sum. So it's called the Riemann sum, named after the mathematician Bernard Riemann, who first wrote it down. So what we want to do now is look at some properties of this definite integral that follow from this formula. So let's look at the next problem here. So here's example 1 involving properties, and we want to compute these 4 different definite integrals. So the first one is the integral from a to b of f of x dx. So here's a. Let's use a color. So here's a, and here's b. And when I say integral, you say area. So it's just asking you for the area underneath this curve. So this area right here. And that says the area is equal to 16. So this answer should be pretty simple. It's equal to 16. And now the next one is asking from the integral from b to c of f of x dx. So now you want to go from b, so right here, to right there. And now a lot of times what you want to do is you say, okay, well the area is 2, so I'm going to write down 2. But the problem is that the area falls below the x-axis. So it actually turns out not to be positive 2, but negative 2. And this follows right from that definition we wrote above. So the integral from a to b of f of x dx is equal to this sum of f of x sub I delta x, I equal 110. Now you don't have to memorize this definition. I just want you guys to see what's happening here. Here you just always remember that if the area is below the x-axis, it's going to be counted as negative by the definite integral. But the reason this is because f is negative. So you basically have a negative number times a positive number, so it's going to give you out a negative when you add them all up. So here, even though the area is 2, the definite integral is going to count it as negative 2. So if you want to, let's look at part C, and let's erase all this. If you want to now take a look at the integral from a to c of f of x dx, so we're going to go from here to here, you can't just add 16 and 2, because the answer is not 18. Because what the definite integral will see is to say, hey, this is positive 16, but this is not positive 2, it's negative 2, so it'll take away 2, and you'll get back 14. Because again, the definite integral sees this area as being negative. Now, to get it to be positive, what you can do is you can take what are called the absolute value. So you take the absolute value of the function, and this is going to change f of x. So if you want to graph absolute value of f of x, if f is positive, it's going to leave it alone. So basically, the absolute value of f of x looks exactly the same as this. But once it goes negative, it just flips it and makes it positive. So it just flips this graph and makes it positive. And so now if the integral from a to c of absolute value of f of x dx is going to be equal to 16 plus 2, because now the function lies above the x-axis and you get 18. All right, so just be a little bit careful. If the function lies below the x-axis, it's not going to be counted as positive, it'll be counted as negative. A nice simple example is if you have this function here, and let's say it goes from minus 2 to positive 2. And it's symmetric. So this side is basically the same as this side, but it has the absolute value. If you take the integral, and let's give this a name, let's call it g of x. The function's g of x. If you take the integral from negative 2 to 2, of g of x dx. I don't know, you don't even need to know what the actual area is. It's going to count up this area here, and it's going to count up this area here. And they're going to be exactly the same, but one's going to be positive and the other's going to be negative, and so they're going to cancel out and give you 0. Right, so just be a little bit careful with these properties of the integral. It sees things underneath the x-axis as being negative, and it follows from the definition. I mean, this is the height. If the height is negative, then the definite integral is going to say that the area, quote, quote, area, say, quote, quote, area is negative. All right, so next thing we want to talk about are how integrals and derivatives are actually connected. So there's actually a link here between an integral and derivative. And first we're going to take a look at an application, and then I'll talk about how they're connected, which is given in the fundamental theorem of calculus. So let's take a look at this application here and walk through it. So it says the marginal cost of a company producing Q items is given by C prime of Q and dollars per item. What does the integral from 50 to 100 C prime of Q dq represent geometrically? So here you can just draw a picture, and you have basically a 50 here and 100 here. I have no idea what C prime of Q actually looks like, but we can just graph something to get an idea. So here's my C prime of Q. And then, you know, if I say integral, you say area, so that those symbols there really just represent the area underneath this curve. So in part A, what I would write is the integral from 50 to 100 of C prime of Q dq simply represents the area under, and this is called the marginal cost function. So you can write either the marginal cost function, or you can write C prime of Q from Q equal to 50 to Q equal to 100, and this is units. So geometrically, it just represents the area underneath the curve between the two limits of integration. And then in part B, what are the units of the integral from 50 to 100 of C prime of Q dq? Now this one is actually a little simpler to answer if you write down what the actual units are. So here's the integral from 50 to 100. You have this C prime of Q, and then you're multiplying by dq. So think for a second here. C prime of Q is dollars per item. So this is dollars per item, and dq is the change in the items, and so this is times items. And if you multiply dollars divided by items, items should cancel, and you'll be left with dollars. So this definite integral is actually giving you back a dollar thing. And if you think about it, what it's actually saying, the dollar thing, what it represents, actually represents the change in the cost from producing 50 to 100 items, which we'll actually talk about next here. So let's look at part C. What does this definite integral represent verbally? So this is another way to say, what does it actually mean? So in part C, I'd say the integral from 50 to 100 of C prime of Q dq, and let's go back to black, we could say represents, since it's a dollar stuff, it actually represents the change in cost from producing 50 items to 100 items. So it represents the change in cost from producing 50 items to 100 items. You can kind of see this if you think about it from the graph, so let's just take a minute, because I think this is kind of important for you guys to see, especially if you're going to have to use or interpret these definite integrals in another class. So this is my c prime of q. So this tells me how the cost is changing with each item, basically. And so down here I have 50 and I have 100. And if you put a number on this thing, so like at 50, let's say you get out, let's say you get 30. This would be $30 per item. And you wanted to estimate, how much more am I going to have to spend between 50 and 100? Well, if it's $30 per item here, and you have 50 items, what you can do is take 30 times 50, so take 30 times the length, which is 50, and you'll notice that the units here are going to cancel, and you're going to get 30 times 50, I believe, is $1,500. So that would be a lower bound to how much it would cost. Of course, you could get an upper bound if you knew how much it costs at 100 items, if this was the graph. So at 100 items, suppose it's actually $50 per item. And then you could take 50 times 50, right, and get the actual square here. And that would, from the picture, that would give you an upper bound. So 50 times 50 is $2,500. But it's the area that's giving you the change in the cost. And so this actually represents the change in the cost from producing 50 items to 100 items. You could also say it's the increase in the cost from producing 50 items to 100 items if it's actually an increase. But the change is probably really a better word to use. And then in part D, so in part D, they actually tell us what the formula is. So here's the formula for the marginal cost function. And so it says if c prime of q is equal to this, then find the increase in cost if the production level is raised from 50 to 100 items. So this is basically saying find this definite integral. So 50 to 100. If c prime of q here is equal to this, so if it's 1.92 minus 0.002 q dq, what is that equal to? Now to do this, I'm going to use my calculator. So take out your calculator and simply crunch this definite integral. So in y equals, hit y equals, and put in 1.92 minus 0.002. Now, of course, you don't have a Q button, so you just hit the X button. You're going to make your window. So now make your window, and your window is going to go from 50 to 100 because your lower limit is 50 and your upper limit is 100. You can zoom fit it then. So zoom fit. And it's going to give you a nice looking graph, and we can copy down the graph here if you want. So the graph starts up here and goes down here. And it goes from 50 to 100. And you want to figure out the area underneath the curve because that's what the definite integral gives us. I say integral, you say area. So on your calculator, you simply hit second trace. It goes to the calculate menu. You go down to the integral f of x dx, hit enter, ask for the lower limit, which is 50. Then it asks for the upper limit, which is 100. You hit enter, it shades in the region, and will spit out the answer of $88.50. So that's how much it will cost to go from producing 50 units to 100 units, or in this case it says items, so 50 items to 100 items. The final thing we want to talk about is the fundamental theorem of calculus. We want to basically see how the derivative and the integral are connected. So down here we have what's called the fundamental theorem of calculus, and it introduces this idea of antiderivatives. So real fast, you can take x squared and take its derivative, which is 2x. But I could also give you 2x, and you could find its antiderivative by going back the other way. So the antiderivative of 2x would be, let's say, x squared. All right, so the derivative goes one way, so derivative goes this way, and the antiderivative goes back. So you can take the derivative of a function, and you can also take the antiderivative, and which will take you back. Now the fundamental of theorem connects these two ideas, the derivative and the antiderivative. And so basically, let's write this down. So the fundamental theorem of calculus, what does it say? So the fundamental theorem of calculus says that the integral, this definite integral, the integral from a to b of f of x dx can be computed by finding the antiderivative of little f. So basically you want to find the antiderivative, which we'll call capital F, and you can plug in the upper limit into capital F and take off when you plug in the lower limit to capital F, and that's going to give you your answer. So where capital F is the antiderivative of f, right? What that means, right, i.e., that is to say that the derivative of f prime, right, with capital F, so derivative of capital F, is actually equal to little f. So let's take a look at some examples. So down here we have example 3 using the fundamental theorem of calculus. So it says use the fundamental theorem of calculus to find the area underneath the graph of the function on the given interval 0 to 2. Right, so what you want to do is you want to find this definite integral. So let's take a look at part A. So we want to find the integral from 0 to 2 of 2x dx by using the fundamental theorem of calculus. So the idea, the fundamental theorem, if you look up here, what does it say? It says basically find this capital F, which is the antiderivative of little f. So can you think of a function whose derivative is 2x? And hopefully you're like, okay, what function, if I take its derivative, right, 2x, and you think, oh, x squared. And so x squared is that capital F, and the way we're going to write evaluate at is we write this line from 0 to 2. So this is said, you know, x squared evaluated from 0 to 2, and then we do what the fundamental theorem says, which is we plug in 2, so you get 2 squared, minus you plug in 0, and you get 0 squared, and that's equal to, of course, 4, right? 4 minus 0. So see the parts and how they sort of line up, okay? So here's my little f, here's my little f, here are my limits a and b, so here are my limits 0 and 2, and of course dx is dx. And then I have f of b, right? Now f is x squared, and f of b would be f of 2, which is 2 squared. And then it's a minus sign, so there's a minus sign. And then f of a, which my a is 0, and f of a is just 0 squared. And so 2 squared minus 0 squared is 4, and so that's my answer. Now I can check this answer with my calculator, which you should always do if you have time. So to check this answer, I can graph 2x, and then make my window go from 0 to 2, and then zoom fit it. And you see the graph of 2x. Now remember, when I say integral, you think area, so I want to find the area underneath this curve. So I can hit second trace, go down to the integral of f of x dx, hit enter, lower limit 0, upper limit 2, hit enter, it'll shade the region in so you see you're finding area, and yes, it's equal to 4, so it checks. Let's do the next one. So on this next one here, I have the integral from 0 to 2 of e to the x dx. And again, I want to use the fundamental theorem of calculus to find this. And so I'm looking for a function whose derivative is e to the x. Right, so can you think of a function whose derivative is e to the x? And hopefully you're thinking, yeah, e to the x. Derivative e to the x, e to the x. And we're going to go from 0 to 2. So it's sort of an in-between step before we plug in the limits. And so now I'm going to plug in 2. So I have e squared. So I plug in 2. And then I always think this is evaluate at, but I think that's like a subtraction sign. So then I'm going to subtract off when I plug in 0. So e to the 0. And so this is equal to e squared minus, now anything raised to the 0 is 1. So I get e squared minus 1. Since they're telling me I'm finding area, you might want to write unit squared to indicate that's actually an area thing. I can also check my answer on my calculator. So if you have your calculator, let's just check it real fast because it's not hard to do. So hit y equals, clear out whatever's in there, and you want to graph second ln, which pulls up the e to the, and put an x there. My window is going to go from 0 to 2, and you're going to zoom fit it. And so there's a graph of my function. Now remember, this is a definite integral, so I say integral, you say area, so it's trying to find the area underneath this curve from 0 to 2. So you hit second trace, go down to the integral of f of x dx, hit enter, lower limit was 0, upper limit was 2, and it's going to spit out not e squared minus 1, but an approximation, so it gives you about, what, 6.389 blah, 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 and you can check it on your calculator, so hit second quit, you can actually see, okay, so second e squared minus 1, is that indeed the 6.389 blah, blah, blah? And it is, so it checks. So I can say this one checked, you know, and this one checks. So I know this is the right answer for part A, and certainly this should be the right answer for part B then.